Right, so last time we talked, so I'm just going to remind us sort of what we did. So we started talking about, so I'll just remind you that our main interest is with the vorticity equation, right? And remember that u, the velocity, or the gradient of u rather, it can be written as some singular integral operators of omega. And last time we talked about how when you sort of change variables, you can write this as a singular part and the regular part. Okay, so our goal is today, so sort of we understood how to deal with the non-local effect in a certain way, that way. And today, I want to start by talking about, generally about stability and blow-up, okay? So, it's just, okay, we're just gonna go straight through what we did. Okay, so what we did last time, so maybe I should have started here. So what we did last time is we figured out a way, as long as you're looking at certain kind of functions. So this is, you think omega is really a function of x to the alpha and the angular variables, right? So you think it's an f is smooth. So for this kind of functions, you can prove a decomposition of this form, right? Okay, so then if you have a decomposition, you should plug it in. So if you should get 1 over alpha terms, but then you could rescale time by alpha, and then you get this, this system. So you get that omega is being transported by its singular part and forced by the singular part of the vortex stretching, and then there is this lower order term. Okay, so this is what the decomposition gives you. And this is, completely general for, you don't need any axisymmetry or anything like that. So, so the idea is that, okay, right? So the idea is that we want to check, so can we get a blow up? So can we get singularity for the alpha equals 0 equation? That's number 1. Number 2, okay, so can we sort of continue to alpha positive? Okay, so that's really the question, okay? Of course, alpha equals 0 doesn't exactly make sense for the original equation, because we also scaled. So really, the kind of thing we're looking at is like that. Okay, so we took this and we sent alpha to 0, and we got an equation like this. So it's exactly what alpha equals 0 means is not that important, but the point is to say that when alpha is 0, you have an equation, and then you can think of the Euler equation as just a perturbation. Okay. Okay, so in terms of this second question, so let's leave the first question for a little bit. So in terms of the second question, how do you go from a blow up for a model? So if you have, something like this, and you have a blow up for this part, okay, how do you deal with this perturbation? Okay, so in theory it should be a little bit complicated because things are blowing up, so this could have a big effect, right? Okay, and so I'm going to talk about 2 ways you can try to approach this question. So one way is basically a fixed point method, and the other is like a compactness method. So these are two ways that appeared in previous works. Okay. Any questions so far about just the setup? Okay. Okay, so I have to clear all drawings. Okay, so the fixed point method. What is the fixed point method? So that as a, this is not really a bad model, right? So let's just take as a model that we're studying the ODE blow up, so Riccati equation blow up, and we add to it, some kind of extra term, which is small. And here epsilon is clearly a small number. And n is some kind of nonlinearity, which we assume is like a bounded operator. And we assume it's quadratic. So a here is a number. And we assume that it scales has the same scaling as f squared. Okay. Does that make sense for everybody? So something I could put for n of f, I could put something non-trivial like n f times the Hilbert transform of f, or f times some kind of Ries transform of f, so something like that. Okay, so okay, but n being bounded does not allow, for example, u times dxf, where u is like an integral of f or something. Okay, that would satisfy both of these conditions, but for this fixed point thing, we're going to assume that n is also like a bounded operator. Okay, I'm not being very precise about what I mean by bounded, but like it satisfies some kind of, like you can find a reasonable space where you have this kind of thing. Okay. Okay. Now, how do we approach this problem? Okay, so first, we should understand the epsilon equals 0 problem very well. Now, this looks like deceptively simple, right? Because it's just an ODE. But we're going to treat x now as like a parameter, and we're going to try to find the stable blow-up of this one, as fun, if you have like functions of x. So, one has to be careful. So if you think about ODE blow-up, you're thinking about a constant, right? Constant just going to infinity, right? So this is actually the most unstable blow-up for the Riccati equation. So, okay, so I don't want to, go too much into this. So you can find this self-similar profile. So you look for a profile like this, so which has a very clear dependence on space and time. Okay, so you plug this ansatz in, and you get this equation. Okay, there's the f is identically 1. That solution is this one. But then there's another solution. So there's actually a continuum of solutions, sort of between this one and this one. And the most stable of which is this one, under smooth perturbations. Okay? Does that make sense? So we can find one self-similar blow. Okay, so then when epsilon is positive, we can, so what do I mean by stable is going to be clear later. Yeah, so stable, just as a question in the chat. So stable will mean something later. Okay, it just means that if you perturb the equation, you get a different behavior. So just as an example, or you even perturb the data. So if you have this one, if you make any perturbation of this, essentially any perturbation, the blow-up will become very different from the straight line blow-up. So if you make a perturbation which makes it look like that, okay, here you have a blow-up for all points, right? So the thing just goes up, right? Here you have a blow-up. At the time of blow-up, you only have this one. So at the time of blow-up, it really looks like that. Does that make sense? So it's a completely different type of dynamic, right? So any type of perturbation, and this really depends on the Taylor expansion near the maximum. Okay, so it's good to think about this deeply to understand things, but I don't want to spend too much time on this. Okay. All right, so now what about when epsilon is small? Okay, so when epsilon was 0, we found a solution. F of xt is, so this is when epsilon is 0. We found a solution like this. Oops. Okay, so we found a solution like this when epsilon is 0. Okay, and now when epsilon is positive, we can hope to find a similar type of solution. So we take as an ansatz this. Okay, so now the reason for this delta of epsilon will become clear later. So if you try it without the delta of epsilon first, which is what you should do, then you'll find that you're going to run into trouble. Okay, so I'm going to save you the waste of time and put the delta of epsilon from there. Okay. Okay, so let's plug this into there. So then we get this system. And now, when epsilon is 0, we can take delta epsilon to be 0, and then we have our F0 is a solution, right? So F0 plus z dz, F0 is F0 squared. So we have this guy. Okay, and now taking, doing what you expect to do, you find F epsilon as a perturbation of F0. So you introduce G plus F0, okay? And then you get, on the right-hand side, a linearization. Okay, so this is just the linearization of this thing around F0. So if you linearize this thing around F0, you get that. Okay? You get this box thing. And then you have other terms. So you have this term, and then you have nonlinear terms. So you have G squared. Okay, G is supposed to be small. It will be like order epsilon. And then you have epsilon times this thing. So this thing should be, there's going to be a non-homogeneous term here, right? So there's going to be a term depending only on F0, and that's what will force G to be not identically 0. Okay? Does that make sense for everybody? Any question? So now we get this equation. So let me erase. And now, okay, n is a nice operator. So all I'm doing is like an implicit function theorem, right? So if L was invertible, so if L is invertible and L inverse n is bounded, it's like a nice bounded operator, then it's clear that you could solve this by contraction mapping, right? You just write G, you just write it as a fixed point. You'd write G. Okay, if L was invertible, we would take delta epsilon to be 0. We'd get G is L inverse G squared plus epsilon n of F0 plus G. And this you can, this right-hand side, you can show as a contraction on some ball as long as epsilon is sufficiently small. Okay, as long as L is actually invertible, and N is a nice bounded operator. There's no problem with what I'm saying. Does that make sense to everybody? Okay, well, the problem is that L is actually not invertible, and that's the reason for this delta epsilon. So let me explain now the next lemma. Okay, so maybe you saw it already. So the lemma is this, that if you're trying to solve L of G as F, it's solvable if and only if you have this condition. Okay, if you want like a smooth solution, you need this kind of like a compatibility condition, okay, or something like that, or so a solvability condition or whatever. And in that case, you can write G in terms of F like this, and the G is bounded by F. Okay, does that make sense? So basically, the idea in how you, so I'm gonna explain how you prove this lemma. I don't know if it's it may prove to be a waste of time. I don't know, but we'll see at the end if I get through everything. But this compatibility condition, this is like a one-dimensional condition, but we have this extra parameter here, right? So basically, you want to use this term. So you want to choose, right, delta epsilon. So delta epsilon technically will depend on G and on N, right? So you choose delta epsilon so that the right-hand side is in the range of L, so that this is solvable. Does that make sense? And then you can do the contraction, okay? All right, so let me just explain to you where this condition is coming from. So it's just, how you understand solvability of these things is just by doing like a Taylor expansion, right? So basically, you know, these are just, so for Z bigger than 0, this is just an ODE, and it'll be perfectly nice and solvable, right? But for Z at 0, there can be some problems that happen. There's some F's for which you can't have a solution if you're starting with Z equals 0. Okay, so how do you see that? So you just start, you know, if you have L of G as F, right? You start trying to compute the Taylor coefficients of G in terms of those for F at 0. Okay, so you evaluate, so L of G is this guy. So if you think about it, so if you're trying to solve G plus Z dz, G minus 2 over 1 plus G is F. Okay, you evaluate at 0, you get minus G at 0 is F at 0, right? So that tells you how you find G of 0. You try to find G prime of 0, and then you run into trouble, right? So if you take the derivative here, the derivative can hit here or it can hit there. We're going to evaluate at 0, so it doesn't matter if it hits there. And then it can, so let me erase that one. So then it can hit here and here, okay? The point is that the derivative part vanishes and you get this thing, okay? So that means that for there to be a C1 solution, you need this to hold. Does that make sense? And once it holds, you can start, you know, solving it as an ODE, as you do normally. Okay. Any question about this? So, okay, so I'm not going to, you just do like whatever it's called, integration factor and all that stuff. There's nothing really deep here. You have to be careful about 0, right? So you have to add and subtract the right quantities, and then you get this formula. Okay, let me just, it's easier to see up here. So you get this formula. And the presence of this f of 0 makes you wonder whether it's, integrable or not, like whether you really can prove L2 estimates. But there's a cancellation when z is very large. So I'm not gonna, because of this condition, this thing is like order of t squared when t is very small, right? So that's why this makes sense. And when z is very large, there's a cancellation between this term and that term. Okay? Does that make sense? So I can go into details about this if someone wants, but I don't think it's super important. Okay. And okay, how do you actually prove the HK bounds? So these are like Hardy inequalities. So you just use this formula. Okay, so you just do some slight generalization of the Hardy inequality. So if you know the proof of the Hardy inequality, it's not a big deal. Okay. All right. So let me proceed. Okay. So that's fine. So now we have a way of inverting L, so long as we satisfy the condition. So let's just remember the condition was what? 2f of 0 plus f prime of 0 should be 0. So L of f is g implies this. Okay. Sorry, L of g is f. L of g is f. Okay, so now you look at this term. So you ask, can you really use this term to ensure this condition? Well, okay, this is the right-hand side. Let's evaluate at 0. So 2 times the right-hand side at 0, that's this part. Right? 2 times the right-hand side at 0 is just this part because z is 0. And then plus f prime of 0, you just get this thing, and then whatever the derivative of that stuff is. Okay? And therefore, you just choose delta epsilon. You just say, I'm going to take delta epsilon to be that number, whatever it is. Right? So now, this is like, you can think of it as like a function. So delta epsilon is like, you can go from, say, h2 or hk into r. Okay, so it's just a number depending on g. And then after that, you can prove it's a contraction. Okay, does that make sense for everybody? So this is not, so this is only useful when the n, so the nonlinearity you're adding is really a bounded operator. So there are a couple of remarks you can make. So first, you don't need that n is actually bounded. So let me state the theorem, sorry. So the theorem is that if n is bounded on hk, for some k greater than or equal to 0, maybe also can assume it's like bilinear or something, then there's a delta, okay, so constant multiple of epsilon, so that this operator k, so this thing, maps b delta of 0 to itself, and it's a contraction, right? If epsilon is sufficiently small. So I should say if epsilon is sufficiently small. Okay, maybe that goes at the beginning. Okay, so some remark is that you don't actually need this boundedness. So you don't actually need that n is bounded. All you need is that this thing is bounded. Okay, so in one dimension, so this this idea was essentially done in a work with Inji Jiang. I may have mentioned it above. And in that case, n did contain a term of this type, but it was one dimension. So it was a term of this type where u was like, so n was like this, and u is something like that. Something like that. Okay, so this is not bounded, but when you take L of n, okay, because you can sort of integrate by parts, and L inverse, and L inverse has some integral in it, you can show that L inverse of n is actually bounded. So that's all you really need. Okay, so in problems with derivatives, so higher dimensional problems, where you have that n has derivatives in it, then this doesn't seem like it works. So I wasn't able to make it work this way if n has really derivatives in it. So then, so now we move to the second way, which is the compactness method. Any questions about this fixed point thing? They're related, but they're really two different approaches. So are there any questions before we pass through this? So this, So the statement is just that in general, if you have equation of this type, and this, this one doesn't need to be f squared. It could have been like n1 of f, right? As long as you have this type of situation where you know that the first equation, dtf is n1 of f, has a blow-up and is self-similar, and the linearized operator is invertible, and that L inverse of n, so the perturbation n is somehow bounded, then you should be able to continue a blow-up for the original equation to a perturbed equation. In general, didn't prove any sort of abstract theorem of that type, but I think you could. Okay. All right. Now, what about in the case where n is really unbounded? Okay, so here's the general philosophy. Okay. So in the case where n is not just some bounded operator, let's come back to equation of this type. And say you want to solve. So I switched the roles of f and g. I'm sorry. So suppose that you want to solve for f, and n you don't have any bound on f on n itself, but that you have a bound of this type. So this is like an energy estimate. So like energy type, right? So if you have like a transport term, so something like UUX, or something of that type. Well, obviously, this is not bounded, but when you pair it with something, right? If you pair it with this in HK, then you can, and K is sufficiently large, then you can bound it. Does that make sense? So actually, this should be a 3 here. I'm sorry, but okay, it doesn't actually matter for this part. But right, so if you have this, and you not only know that L is invertible, but you have this, L is kind of like positive, right? It's not. So this is stronger than the assumption in the implicit function theorem or whatever. So you assume that L is really positive in a certain sense. Then you're still okay. Okay. Then there's no problem again, because one way to see that is if you wanted to, under these assumptions, if you wanted to write an existence scheme for this thing, you could do it as like you could introduce this fake variable tau, right? And then you start to study this equation, right? So then what you try to do is, if you know really that L is what do you call it? Coercive, and N satisfies this bound and similar bounds, if you take derivatives, then you would try to prove two things from this. So you try to prove that f in whatever space you're doing. So if you start with f at tau equals 0 is 0. Okay. So you just solve this equation. So you say that f in x is uniformly bounded, okay, because of these things, right? So this is like a dissipation, right? And you have a small nonlinearity. So then you can prove f is uniformly bounded in tau. And if you took d tau, you don't have any more g, so g is independent of tau. Then d tau f, you should be able to prove that it actually decays exponentially. Okay, does that kind of make sense? So if you took, I mean, the first part is just if you have an equation like that, right? Then you do estimates on f, and you get something like, you get this a priori estimate. Let's see here, g with f minus c f in x squared plus epsilon f in x cubed, right? And then from this, it's easy to see that f cannot grow beyond a certain amount, right? Does that make sense? So you can hide part of this in here, and then g remains bounded. So this is something just a general idea. So you can think about it. Okay. Any question? But so the point is that we're going to go away from trying to get estimates on the inverse to try really get positivity estimates on the linear operator. Okay. Okay. So let's go into a little bit of details on how you actually prove these bounds. Okay. So now let's again start with this thing, and I'm going to introduce a second parameter, mu of epsilon. So this is not really necessary to do, but it makes some things a little bit easier. You have to introduce a second parameter at some point, but I chose to introduce it this way. So remember again, we had a solution of this type. Right, so we had a solution of this type when epsilon is 0. And now when epsilon is positive, I'm going to introduce this ansatz. So okay, it's very close to the original one. And mu and delta are going to be things to be found. Okay. Now, I apologize that I changed delta to lambda at this point. So delta is lambda. Okay, sorry. Okay, so in this case, again, using the scaling and the fact that n is quadratic, so we made some assumptions on n from the beginning. So we plug all of this in and we get again this type of equation. And now we're again left with solving this type of thing. Okay, but this time we're not going to try to invert L. We're going to try to use this kind of idea that I described in the beginning. Okay, so the question is, for this operator, can you do that? So can you take this operator and find a space X on which L of G with G is like G? Right? That's the question. Okay. So this is really stronger than invertibility. The answer is yes. So if you think about it a little bit, so let me not go too far. So there is some obstruction to this. So if you think about this operator, so these two are the estimates we kind of would like to prove, right? So we'd like to prove these two estimates, right? First, that L of G with G is bounded from below, and that the right-hand side, in all this mess, can be bounded like that. Okay? So if we have these two, that's kind of an a priori estimate. So I'll explain that at the end. But the main thing is really this one. How do you do this one? So let's think. So L of G is like this. So if you have a function, so we're really on 0 to infinity, say. If you have a function that looks like that, right? Then L of G with G, right, clearly will be negative. Let's say this is 1. Okay. Because this, there's a competition between these two. For Z small, this gives you good, it gives you positivity. For Z for Z large, this will defeat this term, right? For Z small, this seems to be dominant, right? So somehow, depending on how G looks, this can either be positive or negative if you just think on L2. Okay. Now the idea is that okay, you're not going to try to do a Sobolev space. You try to do a weighted space. Okay, so you try to avoid this negative case I was talking about. So if you work on a weighted L2, so you choose a weight like that, then in fact you can prove this equality. You don't really need equality, but you have this equality in this case. Okay. And okay, by now there are different ways to solve this issue. Okay, you can either get lucky and write down some function that works, some weight, or you can. There are other sort of more involved ways of solving this, but let me not discuss that. Now, the point about this weight is that the problem with this is that you made it extremely singular near 0. Okay, which means that you need the functions you're dealing with to satisfy, if they're smooth functions, you need them to satisfy at least like that, right? Because the norm you're talking about is, so at infinity, you don't really need anything, right? Just L2 is fine. But near 0, you need some extra vanishing, which you don't really know in general. And this is where the choice of the two parameters comes into play. Okay. So if you look up here, okay, all of this stuff, just like in the fixed point method, all of this stuff just has G and F0, right? It doesn't have mu and lambda. Okay, so the idea is just to choose mu and lambda so that the right-hand side evaluated at 0 is 0, and the right-hand side is derivative at 0 is 0, right? That's it. So you have two parameters, mu and lambda, so you just use them like that. So as long as there's nothing, you know, unlucky about this particular function, you can do that, right? So let me do that. So, so this is the function you have at your disposal. And F0, remember, is 1 over 1 plus z. So when you evaluate at 0, you just get minus mu. So you just use mu to correct this condition, right? And you use lambda to correct the other condition. So if you differentiate and evaluate at 0, you get some things in terms of mu and lambda, but you already chose mu, so then you just solve for lambda. Does that make sense? Okay. Right, and now, okay, so this is a little bit of a mess. And obviously, the fixed point way, like the classical way, is always better, but this is a little bit of a mess. But so if you define, you know, this kind of inner product, okay, so you define f and g in x is like this plus some constant with this. You have to be you know, a little bit careful. And this, so this is like stronger than H2. So this is stronger than H2. Okay. And it's equivalent to H2 in the sense that you just need, the only difference is you're forcing f and g to vanish quadratically at 0. Okay. In this case, the lower bound holds. So 3.2 is just L of f with f is bigger than c f in x squared. Okay? Does that make sense? So then, you know, assuming some reasonable assumptions on capital N, like what I wrote, so for example, that n of f with f and x, even though n is like an unbounded operator, that this thing can be bounded by cf in x cubed. So this is usually the case for transport terms and stuff like that. So whenever you can prove local existence without viscosity, usually you have something like that. Okay, so then finally you get your corollary. So this is the main result. So there is a constant and an epsilon sufficiently small so that if you know this, then you actually know this. So if you had a solution, right? So if you had a solution to, okay, so that means it's a little bit complicated how to do this. So the point is that you're just proving like an a priori estimate. So you basically say, assume that there's a small solution of this equation, right? Assume that you do have a small solution. Then, in fact, you have an even smaller solution. Okay? Does that make sense? It's not for all epsilon, because there's just some epsilon like that. Okay? And this is how you prove this is basically what you use to prove existence. So if you believe in the mantra that a priori estimate implies existence, then we're done. Okay. Okay, so this is what I call the compactness method. Are there any questions? So here stable, by the way, so in terms of the question about stable, so stable just means that, so basically I should explain one thing that, so I should explain one thing that here when I introduce these two parameters, mu is really like the, so you can do like a time translation. So somehow if you exhaust, stable means if you exhaust all of the natural symmetry parameters in the equation, then which in this case is really 2. So time scaling and, not time translation, sorry, time scaling and space scaling. Sorry, so this should be an X. Okay, but if you exhaust the two parameters, then you're going to have this kind of situation, right? So really positivity of the linear operator, which means like no unstable modes. If you chose a different type of different profile than the F0 I chose, so say you didn't choose this one, you chose like this one. I think this is another profile. If you chose this profile, okay, lambda will also change in this case, but it doesn't matter. Then you're not going to be able to just, you'd need, I think in this case, like 4 parameters in order to ensure something like this. Okay. So yeah, so the stable just essentially means like the one that's the least unstable. So you need the least of these parameters to fix. Okay. I hope that some of what I said made sense. So maybe we'll take a break at this point and come back in 10 minutes.